As we mentioned at the end of the last video, the method that was taken over Hamilton's was the one put forth by Thomas Jefferson, which we appropriately call Jefferson's method. There are a lot of cases here of us just taking names based on whoever it was that happened to come up with the thing. Where besides putting one over on his rival, Jefferson's method also is known to be more beneficial for the larger states, like Virginia, both Jefferson's home state and the largest at the time, because what it is built around is the assumption that the ratio of population to representatives is the most important thing, and it's built around a special value called the modified divisor, where for this, what we do works in two steps. We find a modified divisor D such that each group's modified quota is rounded down to the nearest whole number. The sum of the quotas is the number of items to be apportioned. Then the modified quotients that are rounded down are what we call the modified lower quotas. And then we apportion each group to its modified lower quota. Where I'll say here that getting that modified divisor D doesn't actually follow a fixed formula. In the book and in the homework, there's this weird expectation that we're supposed to guess and check our way to do that. That's really dumb. I don't want to waste your time with that stuff. So for us, what I'm going to do is focus on examples where we actually have that value given, because it's just silly and not very useful to spend our time saying, oh, is this almost 500? Yes, but we need to be a little bit less than 500. We could do better if we were a little bit less. We need to do a little bit more than, because that's not quite good enough. It's weird. It's not worth our time. So let's just get an example here, seeing how this runs if we have that divisor value from the start. For this example, we suppose that a rapid transit service operates 130 buses along 6 routes. The number of buses assigned to each route is based on the average number of daily passengers per route. Use Jefferson's method with modified divisor D equals 486 to apportion the buses. So, for this, we're given the modified divisor, and if we're given the modified divisor, all we have to do really is find the quotas in terms of that divisor. So we're going to have to fill in a table something like this, where along Route A, we're said to have 4,360 passengers. So our modified quota in that route would be gotten by dividing that 4,360 by 486 to get 8.97, which we round down to 8. So our apportionment there would be 8. Then for Route B, we take that 5130, divide it by 486 to get 10.56, which we round down to 10 for an apportionment of 10. And I'm going to pause here for 1 second, because you're looking at that and you're probably thinking to yourself, hey, wait a minute. That seems silly. We had 0.97 and 0.56. How is rounding down the most efficient thing to do there? Yeah, it is a little bit weird, but that's the system we're working with, so just bear with it. Anyway, from there, at C, we would have 7,080, which you divide by 486 to get 14.57, or a modified lower quota of 14, so your apportionment would be 14. Then D, 10,245 divided by 486 gives 21.08 for a modified lower quota of 21, which is an apportionment of 21. For E, 15,535 divided by 486 gives 31.97. So again, we're rounding down a lot there to get 31 for our apportionment. And finally for F, we take the 22,650, divide that by our value of 486 to get 46 for a final apportionment of 46. So from our quotas, we get 130 for a final apportionment of 130. And to make sure that the values we have up here actually make sense, that they actually work in the way that we expect them to, what we can do first is notice that, again, we have 130 buses along that route, and we are apportioning out all 130 of them. We don't have too many, we don't have too few. And then to also compare the way that we're thinking for this, to compare the way that we're going to get what we expect, well, we can get the standard divisor just for comparison pretty easily. We call that stand div, just to save myself a tiny bit of hand cramping. Where the standard divisor, remember, is the population. So in this case, that's all of the people on the buses. divided by the number of seats, or the number of slots, I guess would be more appropriate here because buses have their own seats and that's confusing. But the number of buses here is 130. So our standard divisor would be 65,000 over 130, or 500. And remember, with our method for Jefferson's method, it's redundant, but that's okay. With Jefferson's method, we're always rounding down, even in terms of that already modified divisor. So, if we're always rounding down, we should expect to want a divisor for Jefferson's method that is less than the standard divisor to make sure that we fit everything in properly. So 486 is reasonable. As I said, actually getting that in practice, if it's not given, is kind of a silly thing with guess and check until you get somewhere that's good, but here it should make some sense that we end up a little bit below. But this obviously has some flaws, and we're going to see a couple more as well, and it would get replaced by Hamilton's method eventually, so Hamilton did ultimately win that one, but wasn't the first thing that they came up with there. The method from Hamilton wasn't the first option we thought about, so let's look at a couple more here that were presented with ideas from John Quincy Adams and Daniel Webster.